Are you ready for this, CTM students? I know I am. Here we go. Chapter 13, practice test. You're going to see 21 problems done here. I will go through each problem the full way through. You'll see the full explanation of it, and I'll be checking my answers as I go, just like you should be as well. If you want some extra help, some extra practice, check out Chapter 13 review in your book on these pages. And for those problems, all the answers are in the back, so you can use that as another resource to help you in your preparation for that test coming up very soon. Alright, so make sure you are ready for that. Let's get right into this now, and let's see what we got here. So for number 1, it says in exercises 1 through 6, for the set of data, we're going to use this set of data, 21, 37, 37, 39, and 46. It looks like it's already in order for me, and so that's going to be helpful when I'm finding the median. But let's just go through this one at a time here. Number 1, the mean. We're going to add them all up and divide by how many numbers there are. So I'll get out my trusty calculator here on the computer and do that. Yeah, I could do that by hand. I could probably do that mentally too, but I just think it's going to be a little bit faster to do this on the calculator. So 21 plus 37 is 37 plus 39 plus 46. That equals 180, and 180 divided by 5 is 36. And so here I'll have 180 divided by 5. My final answer should be 36 for number 1. We are good to go there. Number 2, the mode is number 3. Number 2 is the median. 21, I'm just going to write them in order, 37, 37, 39, and 46. And then I think a good idea, if the list isn't too large, is just to cross them off one at a time from the ends until you get to either the middle number or the 2 middle numbers. In this case, it's just this middle number right there. There's nothing to add and divide by 2 with. You don't have to find halfway in between anything. That is the median for number 2. Number 3, the mode, the number that shows up the most. Well, 37 shows up twice. Nothing else shows up more than once. Therefore, 37 is the mode. Number 4, the mid-range. We're taking the maximum and minimum values. We're adding them together and dividing by 2. So that looks like that. This would be 67. 67 divided by 2 would be 33.5. Number 5, the range. That's the maximum minus the minimum. So 46 minus 21. And that is 25. So that is my range, 25. And then number 6 is standard deviation. This is going to take a little bit more work here. So we're going to have to do a little table here. I think I'm going to put this on the next page. Yeah, I think I'm going to put this on the next page. And I'm going to change my mind one more time. I don't like to flip-flop usually, but I'm going to just fit this over here. So I'm going to do something like this. We'll do our table work over here. But remember, standard deviation, that's not X, that should be S, sorry. Let me just erase that little part right there. So S, and not the sigma, because it's just a sample, not the whole population of something. So this is, we have the square root of the sum of the mean values subtracted from the data values squared over n minus 1. This equation and some other equations I'm not going to make you memorize. I'm just going to make sure that you know how to use them. So you have to know what this is. If I gave you something like a matching choice, you should recognize, oh, that's standard deviation. But I'm not going to make you memorize this equation. You just need to know how to use it. Okay, so what are we going to plug in here? We need to figure out some stuff here. So first of all, we're going to have our x values. I'm just going to make a little table over here. Then we'll have our x minus the mean values. We've already figured out the mean. That was right here. This is the mean. This is x bar. And so that's going to go in there. And we've already figured that out, but we haven't figured this out yet. X minus x bar squared. So this is the deviation. That's another way to think of this. We mentioned that in class as a deviation, and then this is deviation squared. Okay, so we have 5 values. Just going to put them in the same order: 21, 37, 37, 39, and 46. So here it's just these down here are going to be the sums. So here it's just the mean subtracted from the data value. This would be 21 minus 36, which would equal negative 15. This would be 37 minus 36, which would be 1. Same thing here, 1. This would be 3. And then 46 minus 36 would be 10. If you add all these together, they should add to 0 if you did this right, and it looks like they do. So this is a 0. That's a good thing for us there. And now the deviation squared, this part squared. So negative 15 squared would be positive 225. This would be 1, this would be 1, this would be 9, this would be 100. Add that all together, you'd have 111. 111 plus 225 would be 336. Okay, so that's this part right here. That's the sum right here is the same as this part right here. That's the sum of the deviations squared. And so I'm going to plug this in now. Got the square root of 336 over n minus 1. That would be 5 minus 1. That would be the square root of 336 over 4. 336 divided by 4 is 84. So I have the square root of 84. That would be an exact answer. That is approximately, if you type that into a calculator, let's see what that is. The square root of that is 9.165, yada, yada, yada. If you round that off to 2 decimals, it's a good way to go most of the time. Just see what it asks for. So either this or this, I would say, would be acceptable for an answer for that. All right, let's move on to number 7, 8, and 9 all going together here as well. So number 7 says use a set of data, and it looks like we've got 5 rows, 6 columns. So there's 30 pieces of data here. 30 pieces of data to construct a frequency distribution, and we're going to let the first class be 15 to 30. So a frequency distribution, we're just going to do something like this. We're going to have the class, this is number 7, and the frequency. And why that's so crooked, I don't know. But it says the first class is 25 to 30. Have they put these in order for us? Yes, it looks like they have, so that'll make that a lot easier to figure out. What's in that range, 25 to, or 25 to 30? These 5 numbers are in that range. So my frequency for that class would be 5. I want to keep my class size the same. So this includes 6 different numbers here. This is 25, 30, or 25, 26, 27, 28, 29, and 30. That's 6 different numbers included in that range. So here I'd want to have 31 to 36. Next I would want to have 37 to 42. That would include 6 numbers. Don't forget about that 0 digit. That's going to be included. So this would be 37, 8, 9, and then 40, 41, and 42. Here I'd have 43 through 48. And then next, actually, would I have 249? Sorry, sometimes this throws me for a loop. No, we're good. Yes, that's good. So 49 through 54. That would include 6 values. If I'm subtracting these, the upper class limit and the lower class limit here, 30 minus 25 is 5, 36 minus 31 is 5, this is 5, but there's 6 data values in there, so think of it that way. 55 through 60, those subtracted would be 5, but there's 6 data values in there. How high does our table go up here to? It looks like to 66, so the next class would be all I would need to do there. And so let's see what fits into here. 31 to 36. Oh, I missed one right here. I missed 2 right here. Woo, not good. So I need to change my answer over here. Getting ahead of myself there. So all these should be included in that first class. So this frequency, not 5, should be 7. This next one, you've got 31 to 36. That's going to be all these right there. So there's going to be 5 in that range. Here we have 37 to 42. Looks like just 40 falls in that range, so that's just 1. And then next up you've got 43 to 48. That's going to include all of those, so that's 1, 2, and then 5 more, that's 7. And then similarly, this is going to be 5 included in the next group, that next class. 56 and 58 and 58, those all fall in the 55 to 60 range, so that's 3 more. And then finally, this is it. That's 2 more. It almost looks like it spells something, but I don't see what that would be exactly there. All right, number 8, a histogram of the frequency distribution. And I'm going to get out my straight edges for this. I want these graphs to look a little nicer, so when you're drawing these graphs, they should be drawn to scale as best you can. Still use my black though here. And remember, it's always the data values here, the frequency values on the y-axis. When you're drawing histograms, it's always like that. And I'm going to put a grid underneath this to make the graph a little easier for me to draw. Right, so I'm just going to move this a little bit. I have a frequency of 7 as the highest, so I just want to make sure I have 7 blocks here. That would be 1, 2, 3, 4, 5, 6, 7. I could move that up 1. Do that here. Stretch that down just a little bit. Okay, 1, 2, 3, 4, 5, 6, and 7. Looks perfect right there. That'll be just like I'd like it. So space these out evenly when you're drawing your graphs. Make sure you make them nice. I will expect you to make a nice one, a to-scale version on the test you have to take for me. Make sure you're getting that practice right now. Okay, and then going this way, we want to draw, we've got 7 different classes here, so let's see if I have enough there. I've got 1, 2, 3, 4, 5, 6, 7. Yep, I got enough there. I would want to say something or do something like this. I looked at the back of the book. They didn't do this. I'm a little miffed at that, but there would be a break here. We aren't going from 0 and then all of a sudden, boom, there's 25 right there. That's not how it works. But let's do something like that. I'm just going to put that a little closer there. Okay, and so each halfway mark, I'm going to be going up with my bars, and then each one of these marks, the actual grid lines, these are going to be my values. Remember, when you have class sizes like this, it's good to find the midpoint. That's the best way to do this. Find the midpoint of the class, and make that your mark right here. So the midpoint of this class would be, you take these two values, add them together, and divide by 2. So 30 plus 25, that's 55, divided by 2 is 27.5. And keep doing that. The class size is always going to be, the class width is always going to be 5 here, so I want to go up by, or the class width, I'm sorry, is always going to be 6. We have 6 data values there. So I want to go up by 6 as I move up the scale here. I'm kind of squished together here. Why don't I spread this graph out just a little bit? Let's see if I can do this like this. Yep. Sweet. Okay. There we go. And I'm going to get rid of this stuff, make the graph a little easier to read this way. So I'm going to say each 2 bars, or 2 grid lines, is going to be 1 bar going up. So this is going to be 27.5, the midpoint of that class. The midpoint of this class, you'd add them together, divide by 2 again. You can think of it that way. Or you can just add 6, since the class width is 6. So if I added these together, I would get 77 divided by 2 would be 33. I'd get 67, sorry. I get 33.5 if I divide that by 2. I keep going up by 6. So notice that's just plus 6. I can do plus 6 again rather than add and divide by 2. I can just keep doing the plus 6 each time. Plus 6. Plus 6. We still are going. Plus 6. And finally, right there, that'll do it for me. Plus 6. And so as I go up, how far am I going to go up? Well, it depends on the frequency. So the frequency is here. These are the data values here. So here is the class, and then this over here is the, can I write like this? I'm giving it a shot. Frequency. It is tough, but frequency is there. Whew. I'm writing vertically. That was weird. I can't twist my thing here. It doesn't work like that. Maybe it does. Maybe it does. Wait a minute. No, that's no. It doesn't work like that. Sorry. So I have to get some practice at that. Anyways, right here, that's at 7. The next class size, 31 to 36, would fall in this range right here. If you go halfway in between here, halfway in between 27.5 and 30.5 would be, or 33.5 would be 30.5. So right here would be 30.5. That's a good thing, because that means any 30s would go in this bar and any 31s would go in this bar. 30.5 doesn't get included in either one because there aren't any halfway values there. So this goes up all the way to 7 there. This next one goes up to 5. So like that. The next one goes up just to 1. So like that. And then 7 again. Like that. 5 again here. Looks like, I'm glad there's no more 7s here. I'd run into my work that I did there. So 3 and 2 works out perfect there. Okay, so that looks very nice for that. And the frequency polygon of the frequency distribution, I don't need you to draw this all over again. You can just do this in a different color or just overlay it right there for me. So the frequency polygon would just be where the middle of the bars are. You just connect those with straight lines. So you can just do that right on the same graph if you want. I see no problem with that. Should be straight lines. Mine aren't perfectly straight here, but should be straight lines there. You can use a straight edge to draw those in. So that's number 9. Number 9 is the part in red. And let's move on now to numbers 10 through 16, all using the same information here. Alright, we have this mean, median, mode, standard deviation, first and third quartile, 79th percentile, all this stuff given to me in this problem, or for this set of problems. So it says, it's statistics, even I have trouble saying that word sometimes, statistics on salaries. In exercises 10 through 16, use the following data on weekly salaries at Maxwell Mechanical Contractors. And I say even I have trouble with that because I say this a lot. I'm a math teacher, but I still slur that word sometimes. Statistics. What is the most common salary? Most common? You should be thinking mode. So most common is mode. And so what's the mode? The mode is 695. It includes the dollar sign, so we should include that as well in our answer. Number 11. What salary did half of the employees exceed? Well, the mean is the average, but the median is the middle. So what salary did they exceed? The middle, over half would be over the median. So we would say over 670. That would be exceeded here. This is a weekly salary. Okay, I was going to say if that's a monthly salary in this day and age, you're not going to get by. You're not going to get much of a living on that in the U.S. at least. Alright, let's check out number 12 here. Number 12 says about what percent of employees' salaries exceeded $650. So here's the first quartile. That is right there at 25% of the data. First quartile. Think of Q, think of quarters. Quarter 1 would be the first quarter. So what percent exceeded that? I would say about 75%. The rest of the data is going to be above that value. So about 75% would be above that value. Number 13. Get rid of that there. Number 13, about what percent of the employees' salaries were less than 712? And so here's this number, 712 is in the 79th percentile. That means you've got 79% below that, you've got 21% above that. And so what's the ones that were less than? Just said the answer there in what I just said. So 79% below, 21% above. That would be about 79% then being below $712. So that's based on that percentile one. 100%. With percentiles, we think of 100%. So whatever the percentile is, you take 100 minus that, and that's how you would get what's above that. So 79th percentile or 79% below. 100 minus 79 is 21% above. Number 14, the company has 100 employees. What is the total weekly salary of all the employees? And so the mean, remember, is the sum of the data values. So it's the sum. Let me write that a little differently though. So the mean, you can think of it this way, it's the sum of the data values over n. And so they're saying the company has 100 employees, so I could call that n, and then the sum of the data values, the sum of the salaries, in other words, I don't know what that is, but the mean, the average, I'm told is 700. So if I take an equation like this, it becomes a fairly simple algebra problem at this point. We can multiply both sides by 100, multiply by 100 here, and that would tell me what the total amount of the salaries was. This would be my sum of the x values, sum of the data values. It would be 70,000 right there. 70,000. That would be the total weekly salary for all of the employees. Number 15, what salary represents one standard deviation above the mean? So here's the mean, and one standard deviation is 40, so it's a very simple problem there too. A lot simpler than this actually. So I think very, very simple there. You just have to add 700 plus 40. We're going to above the mean, that's why I added instead of subtracted. So $740 would be your answer there. And number 16, what salary represents 1.5 standard deviations below the mean? So this much below, we would take our mean, and now we would subtract because we're going below, and we'd take 1.5 times the number for the standard deviation value like that. It'd be 700 minus 60, which would be 640. Beautiful. We're getting close. I know some of these last ones are going to take a little bit longer though. So let's check them out. Let's see what we got. 17 through 20. We're going to use the mileage of 5-year-old cars is normally distributed with a mean of 75,000 and a standard deviation of 12,000 miles. Okay. So this is a normal distribution. We should be thinking like this. This is just a side note, but think of that normal curve again. We're going to have the mean value. We're going to have standard deviations. We're going to have one standard deviation away. We're going to have two standard deviations away. We're going to have negative, maybe -2. We're going to be thinking about this, what the area is under these things. It's this type of problem here, it looks like. And so what percent of 5-year-old cars have mileage between 50,000 and 70,000 miles? We're going to have to find some z-scores here and go back to that table that we had seen in lesson 13.7. Right, so I have the table pulled up here from 13.7. We're going to be using this table. We're going to be using the fact that z-scores are this x, the data value, minus the mean value over the standard deviation. And again, we use mu and sigma now instead of x bar and s because we're talking about an entire population. We're saying the entire set of data fits within this normal distribution style. Alright, so here we have z equals the data value minus the mean value over the standard deviation. So we're going to think of that. It's here, it's told, or I'm told that this is the mean value. The mu is 75,000. And the standard deviation, that's this part, is 12,000. So it's just a matter of plugging in these values into this equation. So Z value for 50,000 miles is going to equal 50,000 minus the mean value is 75,000 over the standard deviation, which is 12,000. This equals negative 25,000 over 12,000. You could cross off the 3 zeros with the 3 zeros there, and then that, think of that in a calculator, would be the fastest way to do this. I mean, we could do this with long division and whatnot, but I'd rather avoid that if I can. So we have 25 divided by 12, that's 2.083 approximately, so this would be negative 2.083, so approximately negative 2.083. I'll keep it an exact number for now, so I'll get rid of that approximate symbol and put exactly equal to that instead. And I want to find Z of 70,000 because I want to find the range here, the values in that range. So 70,000 minus 75,000 over 12,000 equals negative 5,000 over 12,000. Again, you can get rid of 3 zeros here and here. Put 5 over 12 into a calculator. 5 divided by 12 is 0.416 repeating. So 0.416 repeating. So we're trying to figure out, okay, with 17, I'm going to draw the graph here. So that means it's that many standard deviations away from the mean. So we're going back to here. This is the original score. I'm just going to put the z-scores in here. So we've got a z-score of 0.416. This is negative though, sorry, that should be negative 0.416. So we're going back about to there. So negative 0.416 repeating, and here I've got a z-score of negative 2.083 repeating. So I go back to my table, my z-score table, and I'm going to find those values. I'm going to find negative 2.083. I'm going to find the positive of that, and I know that the positive is the same value. It would be the same because it's symmetrical. It's the same as the negative values over here. And so I'm trying to figure out, let's do this one first. How much of the area is included from 0 to 4, negative 0.416? How much of the area is included from 0 to negative 2.083? And then I'm going to subtract those two things to get this value out. What I'm trying to figure out is what lies in this range right here. So this goes with the 50,000, sorry. This is the 50,000 miles. This goes with the 70,000 miles. This one right here, that's the original. I'm drawing the original in red. This is just to help us determine what it is, but that is the mean value. That's 75,000 right there. So what's in that red range? Let's see what we got here. So let's find negative 0.416 repeating. Let's see what that gives me in the table here. So that's the same value or area value as 0.416 repeating. That would be rounded off to 0.42. So we're going to use this. We're going to round things off. We're going to use 0.163. Okay, so that's the area from 0 to negative 0.416. I'm going to put that in green over here. I think you should be showing some work like this in your work somewhere. We got to think of it or think it through like that. So now I said all that stuff, I forgot what it was. 0.163, okay. 0.163 is right there. How much is from here to here? So that would be from 0 to 2.83. From 0 to 2.83. I'm looking for 2.083. Looking for that, so that's 0.481. 0.481 in the Z table there. 0.481. And just trying to color code things. You don't have to, but I'm trying to do that here to make it easier to see what's what. And so this value right here is going to be this one minus this one. Because I want to take, this is everything from here to here is 0.481. and then this little sliver is 0.163, so what's left over would be those two things subtracted from each other. So this minus this, put that into a calculator and see what I got. So 0.481 minus 0.163, that's 0.318, which would be the same thing as 31.8% of the data. And that jives with what the book says, so we're good to go on that one. All right, number 18. I'm going to be using a similar idea here. I'll just segregate those two things there. So it's still the same values here and here. What percent of 5-year-old cars have mileage greater than 60,000 miles? Okay, so let's find the z-score for 60,000. We're going to have to find that first of all. We're still using this idea, so it's 60,000 minus 75,000, the mean, over the standard deviation is 12,000. This would be negative 15,000 over 12,000. Get rid of the 3 zeros here and here. This would reduce to 5, negative 5 over 4, which would be the same thing as negative 1.25. And so this is your z-score. Let's draw a graph to help us visualize what is going on here. So here's the mean value right there. I'll put the z-scores right there. The originals I'll put in red. I'll keep it consistent with what I was doing here. So I want to find this negative 1.25. That's about right there. So negative 1.25. That went together with the z-score of 60,000, or with the regular score of 60,000. That was my original value right there. I know on the notes I flip-flopped those, but we can think of it like this too. It doesn't matter if I have them flip-flopped. This is 75,000 as the mean, the 0 standard deviations away from anything. So what I'm saying is, or what I need, is the amounts, what does it say, have miles greater than 60. Okay, so that's everything here plus everything here as well. So this part, I know everything above the mean, that's 50% of the data. So right here, this is 50% of the data. And then this part, that's what I need to figure out. So this from 0 to negative 1.25 is the same as from 0 to positive 1.25. That's a simple look at the table here. Let's figure out what I have. Where's 1.25? Here it is, and that gives me 0.394. 0.394 is what I have right there. So 0.394, which is the same thing as 39.4%. So I'm just going to take this and add them together. So 39.4 plus 50, that's 89.4%. Okay, I'm running out of space here, so I'm going to add another page in between here. Right, this is going to be number, what am I on, 19? 19, yes. So 19, what does it say? 5-year-old cards, mileage greater than 90. So greater than 90, I'm going to have the same sort of graph, but I'm going to have something over here above the mean now, and just this little sliver over here. So I need to figure out what's the z-score of 90. I haven't calculated that yet. So the z-score for 90,000 is going to equal 90,000 minus 75,000 all over 12,000. Data minus mean over standard deviation, again, is what that is. You got 15,000 over 12,000. This would go away there and there. You'd have 15 over 12, which is 5 over 4, which is 1.25. Now that looks familiar. We've already figured out what that was in this part. For 1.25, it's the same as negative 1.25. So if I were to draw my graph, I would know that that part here would be 39.4%. Let's draw the graph though, for those of you that are just like, what is he talking about? I have no idea right now. This is a z-score of 0. This would be about 1.25 here. These are my z-scores again. And my original scores I'll put in red. This was 90,000. This one is 75,000. Right, and so what I've calculated before would be the area from here to here. So this part right here is 39.4%. I've already figured that out, no need to do that again. I know from here, continuing on forever, 50% of the data is above the mean there. So I'm going to take this and this, I'm going to subtract those two because I need to find this part. So I know it's 50 from here on forever. I know this part of it is 39.4. So to figure this out, I'm just taking 50 minus 39.4 to get my answer of 10.6%. And then finally number 20, let's see what 20 says. If a random sample of 305-year-old cars is selected, how many would have mileage between 60,000 and 70,000 miles? So we're going to use the z-scores for 60,000 and 70,000. We already determined what those were though. It was negative 1.25. It was negative 0.416. So I'm just going to rewrite those things down. The z from 60,000 was negative 1.25, and the z-score for 70,000 was 0.416. So if we were to draw a graph again to help us visualize what's going on, let's do that. That's the original scores. This is negative again, sorry. So we're going to have another value something like that, and then another one something like this. We're trying to figure out this area now from 60,000 to 70,000 is going to be from here to here. So we're trying to figure out what's this area first. Once we know that percentage, we can just multiply that percentage by the number of cars that we're looking at, a random sample of 300 cars. So it's just one extra step after we got this figured out. And so my z-scores here, put those in again. That's this, that's this. These are the z-scores. The original scores, I'll put those in again one more time. I don't feel like I have to, but just in case it helps you. That's 70,000, and this one is 75,000. Okay, and so I know from here to here, I've already calculated what it was from 0 to 1.25. I've done that a couple times actually. This is 39.4% from there to there. And then this little chunk from 0 to negative 0.416, we rounded off to 0.42. That's the same thing as what we had over here. Here it is. So from here to here, that was 16.3%. So this part's 16.3%. So to figure out this part, that part right there is going to be those two things subtracted. So it's 39.6.4, sorry, I was going to say 0.64, but that's a 4. 39.4 minus 16.3, that is a grand total there of 23.1%. And so now we're taking what is 23.1% of 500. That's the same thing as 500 times 0.231. We put that into a calculator. Let's see what we get. 500 times 0.231, and we get that. Did I do that right? That is our answer. I may have done something wrong here. Let me check my work. Yep, I see my mistake there. This was not 500 cars. Read the question, Mr. Ryder. What does it say? 300 cars. Sorry about that. That should be a 3 right here. That should be a 3 right here. So 23.1% of that. Let's try that again. So 0.231 times 300, not 500. There we go. That's more what I was expecting. So that's 69.3, approximately 69 cars then, if we're going to round that off to the nearest whole car. That'll do it for us. Okay, one more, but it's going to be a long one. Alright, 21, it's got 6 parts to it. We're so close, yet so far away here. 21. The following chart, this is the elderly U.S. population. The following chart shows the percent of the U.S. population that was age 65 and over for the years 1970, 1980, 1990, 1995, and 2000. Where the column labeled year refers to the number of years since 1970. Okay, so this is the years since 1970, and this is the percent of people that were 65 or older. So it's getting higher every year until more recently, and then there's a little drop off here. Maybe people are eating less healthy, less healthful. What's right there? I'm not sure. But that's why I teach math and not English. But I do like to try to be grammatically correct too when I can. You can help me out there. Healthy, healthful. I think I would have a good little debate with some people there. Healthy or healthful. But choice A, or not choice A, but part A, to number 21 here, construct a scatter diagram placing the year on the horizontal axis. I'm going to draw a grid again, or overlay this, underlay this with the grid so that it's easier to make a nice graph. You should be making a nice graph yourself. Okay, so I'm going to get out my straight line tools, and I'm going to be going up to 30. I'll go in increments of 5. That looks like a good way to go. And then my percent, looks like I can start close to 10 and go up to 12. I'm not going to need too much there. So I'm going to say like going up by 0.5%, starting at 9.5%. I'll put a little break in there. It seems like a good way to go for me. So I'm starting here, 0, that would be 5, 10, 15, 20, 25, 30. I'm going to just double this, make that twice as big so it's even easier to read the graph. So I'm going to go about that big right there. It's going to be my horizontal line there, and I'll draw my vertical part here. Okay, that should be pretty good. This is going to be 0. I want to include a little break in the action here, so I'm going to say there's my line break, and then starting here, let me say starting here, we'll say this is 9.5, this is 10.0 or 10, this is 10.5, this is 11, 11.5, 12, 12.5, this would be 13. I'll expand that one more so I can squeeze a 13 in there. There we go. So this will be 13 right there, 13.0. Not 130, 13.0. And then this way we're going up increments of 5. I'm going to skip 2 and call that 5. So 5, 10, 15, 20 years after 1970, 25 years, and finally 30 years right there. So a scatter plot, scatter diagram, placing the year on the horizontal axis. This is my X, my horizontal, this is my Y, my vertical. This is the years after 1970. And this part up here, this is the percent of the population. I'm not going to try to write that vertically again. Percent of the population over the age of 65. So give your graph some good labels. Make sure you know what's what. Make sure the people that are looking at it know what's what. This would be at 0 years. You're at 9.8%. So right about there. At 10 years, that's 11.3. So approximately, this would be 11.25, right halfway in between. So just a fraction, just a little skosh above that. Skosh, it's back. Skadoosh. 20, 12.5. There's that one, right on the crosshairs there. 25 is 20 or 12.8, just a little higher than halfway between these two, and 30, 12.4, just underneath the 12.5 line right there. And so it looks like, yes, it looks like there's this correlation. It looks like it's fairly linear. It does drop off here, but we could draw a line of best fit close to that. We're going to figure that out probably as we go through this problem. I haven't done this problem yet. I'm doing this for the first time, just like you probably are doing this for the first time, this particular problem as well. So we constructed that, and that's good. For part A, we're going to use our scatter diagram to determine whether you believe that correlation exists between the year and so on. So I would say, just looking at that, yeah, it looks like it, yeah, of course, right? Yes, it looks like it's going up as I move from left to right in a fairly linear manner. So something to that effect. The book, if you look in the back, it just says yes, but it says to explain here, so I'm a little disappointed in them. So this is a yes. They didn't give a good explanation. I will give mine here. It appears the data is related with, I would call that pretty strong. That looks pretty strong to me, with a strong positive correlation. Positive, we are talking linear correlation, so I'll even add that in here. So looks like it's related with a positive linear, strong positive linear correlation. Part C, determine the correlation coefficient now. So this is where we get out that ugly looking equation. We're going to have to figure that out. I'm going to do this on the next page. And I'm going to copy this so that I have the information there as well. And so what was that ugly looking equation here? This is going to be part C, but it's actually pretty easy to use. It's just rather tedious. This one right here, am I going to make you memorize this? Of course not. I am not going to do that to you. No, you don't have to memorize this. You should recognize, oh, there's that R1, that's the linear correlation one. Yes, that's the one I'm supposed to use, but I'm not going to make you memorize that whole thing right there. That's not important to me. It's important that you know how to use it. So let's write that down. We have R was, and even I don't have it totally memorized yet, I'll be honest with you. I would be lying to you if I said I got it totally down 100%, no questions asked. I want to look at this myself too. So minus the sum of the x's times the sum of the y's, that goes all on top. We have this over the square roots of, I think this was the number times the sum of the y's squared pieces, or the x squared pieces. Let's see if I got this. I'm going to do this without looking. X squared minus sum of the x pieces squared, and then the other one, I think, if I remember right, is, it looks exactly the same as that with y's instead of x's. Am I right? Yes, I am. I got it. Okay, so I got that part at least. So times n, and then the sum of the y squared pieces minus the sum of the y pieces squared. So all that said, we need to actually figure out what these things are. So why don't I do that down here? I'm going to make a little table for this. Looks like I've only got these 5 things to worry about. So I've got my values here. So remember, going back to 13.8, this is how we tackled that sort of stuff. Okay, there we go. So we tackled that in this manner. We drew a table. We found the x's, we found the y's, we found all their sums down here. All of these values were important because we had to plug them into the equations here. Are you going to have to do something like this on the test? Yes, I'm going to try to keep it pretty simple, nothing too huge to do, but you're going to have to add together maybe 3, 4, or 5 things, find if there's a linear correlation. I'll try to not make it any higher than 5 if I can remember to do that. But let's see what we got here. I almost want to just copy this. Nah, I'll make a new one. So x, y, x squared, y squared, and x, y. I need to do that here. X, y, x squared, y squared, and then the xy parts. And then this is going to be the sums. So this will be down here. These are the sums. And I'm going to put some yellow lines in here just to make it easier for you to see. So that'll be 1, 2, 3, 4, and 5 there. I probably should have just started off like that, huh? Oh well. I'm good. This will work. Okay, so x's, these are the year values. This is my independent variable. These are my dependent variables. We're saying the percent depends on the year. So this was 0, 10, 20, 25, and 30. If I add all those together, I've got 30, I've got 60, 85 for the sum of the x values. The sum of the y values, that one I'm going to have to use a calculator on, it looks like, or it'll be a lot easier if I do. So 12.5, 12.8, 12.4. I'm going to add all those together, see what I get. So 9.8 plus 11.3 plus 12.5 plus 12.8 plus 12.4. 58.8 it is. And now the x values squared, that's 0, 100, 20 times 20 is 400, 25 times 25 is 625, 30 times 30 is 900. If I add all that together, this would be 500, this would be 1400, that would be 25 right there. The y squared pieces, I'm going to figure that out with the calculator. 9.8 times itself is 96.04. 11.3 times itself is 127.69. 12.5 times itself, 156.25. 12.8 times itself, 163.84. I want to double check that one. I didn't see if I typed that in right. Yeah, okay. And then 12.4 times 12.4, that is 153.76. 153.76. Let's take the sum of all those values and see what you get for y squared. 96.04. Oops. 04 plus 127.69 plus 156.25, 163.84, and finally 153.76. I'm just going to double check, see if I type those in all correctly. Looks good, looks good, looks good. Okay. 697.58. 697.58. And then finally the xy values. X times y, that would be 0 right there. 10 times anything, you just move the decimal one spot. 10 times 12.5 would be 125, so I multiply that by 2 more. That would be the same as times 20, so that would be 250. And then these other two I'm going to use a calculator for. So I've got 25 times 12.8, that's 320. And finally 30 times 12.4, 372. Add all these values together. 372 plus 320 plus 250 plus 113. No need to type in plus 0. That looks good. And that gives me 1,055. 1,055 right there. So now I just need to plug stuff in. The n, I have 5 terms right here, so that's going to be a 5. The sum of the x, y values, that's right here, that's 1,055. This minus the sum of the x values is 85. Sum of the y values is 58.8. And now I'm going to have this over. You have 5. Sum of the x squared values, 2025. Minus the sum of the x values, 85, squared. This times, same thing with the y values there. So 5 for the n. Sum of the y squared values, 697.58. Minus the sum of the y values is 58.8. And you're squaring that. Okay. So that big mess gives me, let's see what we got, 5 times 1055. I'm going to do this piecewise. I've got 5275 minus 85 times 58.8. If you want to type this in all at once, you got to be really careful that you got your order of operations right. Parentheses, incorrect places. Don't forget, it's like this is in invisible parentheses here. It's like it is down here. It's like everything in the square root is as well. If you don't include those parentheses and you try to type it in all at once, it's going to be an incorrect answer. So you got to be really careful if you're going to do that. So this is 4998. This would be this part, 5 times 2025, that's 10,125, and then that minus 85 squared, 85 times 85 is 7,225. So we have this times, it's a decimal right there, 5 times 697.58, 3,487.9 minus 58.8 squared, 58.8 times itself, that's 3,457.44, 3,457.44. If you had this number being bigger than this number, then you know something is off, because you're never going to have, with these problems, you should never have a negative number under the square root. So that's a way to verify your answer somewhat, not completely, but somewhat. And now let's simplify the parts that we have together there. 5275 minus 4998 is 277 on the top. This would be right here, 10,125 minus 7225, 2,900. This times these two subtracted from each other, 487.9 minus 3457.44, it's 30.46. And now let's put this into a calculator. Think of parentheses being here, though. We have to multiply these two things together first before we would divide that by or into 277. And so when I type it in here, I'm going to figure what this is out, or figure what that is first. So 2,900, square root of 2,900 times the square root of 30.46. Let's see if I do that way. Yep, that's good. That equals right there 297.21. And so I'm going to take 297.21 and divide 277 by that. So 297.21. I used approximately equal to now because I rounded. That next digit was a 0. And then a 3. Why don't I give a couple more digits here? So a 0 and then a 3 and then a 6. So I'd round that off. This will give me a slightly better answer if I round a little less. And so let's do that. 277 divided by 297.2014. So there it is. Very strong correlation, in my opinion. 0.93 is the correlation coefficient there. If you round that off to 3 decimal places, that's the way our book has it here. So that would be 0.93 and 19. So definitely rounding that off to a 2. So this is part C of 21.932. Part D should be a little bit easier here. Determine if a correlation exists. I should have enough room, I think, for that right there. At alpha at 0.5%. So let's go back to 13.8. Find that table that we used for that, the correlation coefficient table here. Get rid of that in there. We're saying my data, my number of values was 5, and we're at this one, not at this one. It looks like it wouldn't work if it was at 0.01. So here, though, at 0.01, 0.05 at 5%, it is going to be statistically significant. That's not the way I want to say that, but it's going to be a less than 5% chance of this not being correlated. So there is a correlation there. The way they're wording this, whether a correlation exists, yes. If you had to give a reason, you would say because 0.932 is greater than or equal to that cutoff value, which is 0.878. Oops, wrong one. 0.878 for n equals 5. That's our number of values there. And alpha value of 0.05 in table 13.8. Okay, we're getting closer. We're getting there. Part E, assuming that this trend continues, determine the equation of the line of best fit and the year and the percent, between the year and the percent of the U.S. population age 65 and older. Okay. So I'm going to copy and paste one more time here. There it is again. So part E, assuming the trend continues here, equation of the line of best fit. So going back to 13.8 for that, not that, but that one. There we go. So y equals mx plus b. You're going to use m as this and b as this. So we need to use this stuff again. Again, something, of course, not. I'm not going to make you memorize that. I just need you to know how to use that. And so let's figure out what that is. So we're going to have for parts E, y equals mx plus b. I'm going to have to go back to that myself because I don't have it memorized myself yet. So m is the n times that part. Okay. I said okay, but now I forgot already. xy. Okay. Sum of the xy's minus, we've got sum of the x's times the sum of the y's. You have all that over sum of the x squares times n minus sum of x's squared. Let's just double check that. Yep, that looks good. And b equal to that. So the sum of the y value minus m times the sum of the x value over n. Okay, I guess I didn't have to put that in parentheses, but I did. That's fine. Either way is fine with that. Extra parentheses never hurt anybody, but missing parentheses definitely did. Well, I guess I shouldn't even say that though. Sometimes people put extra parentheses in they put it in there in the wrong way. I am getting off track here though. Let's get this answer. Let's figure out what this is. So part E, we've already done these calculations. I don't want to do them again. I don't think you want to do them again either. So the sum of the values there, I've got this part here. I'm just trying to color code, make it easier to see that part. Simplified in the end to 277. So I'm going to use that same work and just write in that was 277. And then this, the sum of the x squared, all that stuff, that's the same thing as what we have under the square root right here. So no need to do that work again. That ended up being 2900 in the end. So right here, that should be over 2900. Alright, so m is going to be, if I take 277 divided by 2900, that should give me my answer. It looks like if I round that off, that would be about 0.10 right there. So approximately 0.10. And my b, the sum of the y values, going back a couple of pages there, the sum of the y values, why did I go back? There we go. Sum of the y values, 58.8. minus m is this, 0.10, so that goes in right there, times the sum of the x values is right here, 85, over n is 5. Plug this stuff in to a calculator. Okay, let's see. This one, I could simplify this first. 58.8 times 0.1 moves the decimal over 1 spot to the left. And then this would be, I could keep simplifying this. Think of this in parentheses. We've got to do that before we divide. That would be 50.3 divided by 5, which gives me 10.06. If I round it off, looks like the book's rounded off to 1 decimal place, so they said 10.1. So we're going to use that, we're going to use this. I'll get rid of that 0 and just round off to the 1 decimal place like the book has done, and say that 0.1, that's my slope, so 0.1, y equals mx plus b becomes y equals 0.1x plus b is 10.1. That's my equation. And we're going to use this. It looks like we don't have to plot it. I could plot that. If I went back to the graph here, 10.1, you'd have, I'll just roughly sketch that real quick. So you'd have 10.1, you'd be going, the slope is 0.1x. So every time you go up 0.1, you'd go to the right 1. If you went up 0.5, you'd go to the right 5. So you have a point right there, up another 0.5, go to the right 5, and so on. That pattern would continue. So if you were to graph it, just as a side note here, you didn't have to graph it, but it would look like that, and you notice those, if you take the vertical distance away from that, that's the best way to do that. That's the way where they are the closest to that line as a whole. And then part F, though, we're using this to predict in 2010 or 40 years after. So we're going to plug in, this is simply a matter of plugging in 40 into the equation here. So this is not showing up on our graph here, but it would be out to here. Here you'd have 40, then you'd be going up to here, the graph would continue up here, and you'd be saying whatever that value is across that way, which we can find using this equation. What am I doing? There we go. So 40 plus 10.1, this would be 4 plus 10.1. So the predicted value would be 14.1% of the population would be over the age of 65 in 2010. Seeing that it's past 2010, I guess we could go to a data book and figure out, or to a website somewhere, find the data for this and see if that was actually true, see if it actually held fast to what we thought it would be according to the linear correlation model that we have here. Alright, 21. Thank you, 21, for making that video about 30 minutes longer than it was before we started that. But hey, that's what we got to do, that's what we got to know. For the test, this is going to be something like this on the test, yes, something like number 20 on the test, and 16 or 17 through 20, yeah. That's the harder stuff, but that will be, since it's harder to do, since it takes longer, it's going to be worth a little bit more than some of these easier problems. These ones, super fast to figure out 1 through 6, really fast to figure out most of these values as well. But expect your test to look something similar to this. Might be some different questions that we talked about in the notes or in the book that come up, but for the most part, it will look very similar to this. Let me know in class if you have any questions, and I hope you do well. Remember, again, to use those review problems as extra practice. All the answers are in the back for those as well. Good luck, study hard, and I will see you soon.